The insect mouthparts are routinely categorized into 4 sections. There is the mouthpart, the lower mouthpart, or mandible, and there are 2
What was that? Everything we saw and felt and heard was energy being transferred. Energy stored in concentrated form in explosives has been released and transferred as light, a shockwave, heat and sound. So what is energy transfer? Energy transfers from higher energy levels to lower energy levels. Energy cannot be created or destroyed. The total amount of energy remains the same. As it transfers from a high energy level to a lower one, it spreads out and becomes less concentrated, less useful. Can you think of any examples? There's concentrated energy stored in that weight, potential energy. The higher it is, the more potential energy it has, due to gravity. How could that energy be transferred to another system? Watch the waves. Now everything's gone quiet. If energy can't be created or destroyed, where's it all gone? When the weight was dropped in the tank, some of the potential energy was transferred as sound, in moving the water, in raising the level of the water in the tank, even as heat, and the sum total of all this diluted energy is equal to the potential energy that was concentrated in the weight. When energy transfers from a higher level to a lower level, it makes things happen. Now the energy has become less concentrated. It's still there, but it would be difficult to detect or measure it. When energy transfers from a high level to a low level, it can be used to do work. It takes a lot of energy of movement, or kinetic energy, to wind up the crossbow. Where's it going? Some of it is transferred as potential energy, stored in the flexing of the bow, ready to be transferred back to the arrow as kinetic energy. We've just seen a series of energy transfers. Could you list them? A lot of kinetic energy is transferred to the bow as potential energy. Some of that potential energy is transferred as kinetic energy to the arrow. Some of the kinetic energy in the arrow is transferred to the air while it is in flight, but most of it is transferred to the target, until finally the energy is so spread out, so dilute, that it can no longer be detected or do very much. Nobody knows exactly what energy is, but we can usually tell when energy is being transferred, because energy transfer makes things happen. Here's potential energy stored in fuel, being released in a chemical reaction and transferred as light and heat. How is energy being transferred here? Or here? Or here? What's happening here? How is energy transferred in a clockwork mouse and in a ginger tom? What do all these processes have in common? As concentrated energy becomes more dilute, it can do useful work. What work is being done here? Almost everywhere you look, you'll find energy, or energy being transferred, even in a cup of cold cocoa. The cocoa particles are moving. They're being knocked about by even tinier water molecules, which have kinetic energy, like the arrow we saw earlier. This is called Brownian motion. Now what's happening? The kinetic energy of the water molecules was increased by heating the cocoa. What would happen to the molecules if you left the cocoa to cool? The movement of the cocoa particles slows down because the water molecules have slowed down. What would happen if the temperature kept on falling? A difficult question. In the meantime, let's see what's in the fridge.
15 degrees Celsius and falling. 10 degrees Celsius and falling. -10 degrees and stable.
Ice. Water in crystal form, with all the water molecules locked into a three-dimensional lattice. The molecules aren't moving around much, but they're constantly vibrating. They have a small amount of kinetic energy. What happens if their kinetic energy is increased? This represents a solid. A liquid and a gas. What does that tell you about the relationship between kinetic energy and the differences between solids, liquids, and gases? In a solid material such as ice, molecular movement is limited. Solid objects keep their own shape because the molecules stay in place, vibrating. If we add energy, the speed of vibration increases and breaks the bonds between the molecules that hold the solid together. They mix and mingle. The solid becomes a liquid which takes up the shape of its container. What happens if we add even more energy to the system? If we add enough energy to the system, the liquid turns into a vapor which fills the container. This relationship between temperature, structure, and kinetic energy can be made to do work. Any idea how? This lump of metal doesn't look as if it's going to do anything, but add a little heat energy and the water in the boiler turns to steam. The molecules of H2O in steam contain a lot of kinetic energy. As they collide with the walls of the cylinder, they exert force on it. The kinetic energy in the steam is transferred to the piston, driving it down the cylinder. And what has happened to the H2O molecules? Finally, the movement of the piston is transmitted to a wheel, which could be used to do work, such as drive steam engines. Pump high-pressure jets of water. Drive a lorry. Or turn a carousel. Welcome to William and Doris Carter's traditional steam-driven mobile fair. Every ride in the fairground is powered by a coal boiler, turning water into steam. Which drives the machinery. Which does the work. Although the customers probably think of it as play. But enough of this frivolity. Now we'll look at a more serious use of steam, such as lifting an upright piano. Here, the kinetic energy in the steam engine is being transferred to the piano as potential energy. The higher the piano, the more energy it has. Could that potential energy be used to do work? How would you use it to drive a machine, such as a clock? Braking cars uses large amounts of energy, and doing it by hand is very time-consuming. Can you think of a quicker way of doing this? How many ways do you know of wrecking a car? One way of wrecking a car is to use explosives. In this case, the explosives are activated by a small electrical current.
Stand by. Firing.
That was a ½ kilo of plastic explosives. How do they work? Where does the explosive energy come from? Let's look at a very simple explosion. This is hydrogen, the lightest of all the gases. And in the cylinder on the right, the gas chlorine. The white cylinder contains hydrogen and chlorine mixed together. Add ultraviolet light, and a lot of energy is released. What happened? Here's a molecule of hydrogen. It consists of 2 hydrogen atoms bonded together. Here's a molecule of chlorine, 2 atoms of chlorine bonded together. Add ultraviolet light, and the end product is hydrogen chloride. How is it formed? It takes energy to break a bond. When the bond forms again, the same amount of energy is released. Hydrogen and chlorine. It takes nearly 200 kilojoules to pull a mole of chlorine molecules apart, and roughly 400 kilojoules to pull a mole of hydrogen molecules apart. When the hydrogen atoms react with the chlorine atoms to form 2 moles of hydrogen chloride, 800 kilojoules are released. The net result is that 200 kilojoules of energy are released, very suddenly, as an explosion. Let's look at that again. The hydrogen and chlorine molecules have a certain energy level. Adding energy in the ultraviolet light breaks the molecules apart into atoms. When they react to form hydrogen chloride, the energy given out is released as the heat, light and sound of the explosion. Buses, trains, and the people who use them. Heat, light, sound, explosions, such as the controlled explosions that drive the engines of cars. Everything that happens depends on energy transfer. Remember, energy transfers from high levels to low levels, becoming less and less useful as it does. So finally, will everything eventually run down?